Okay, welcome back. So what are we going to do? We're going to look at a simple two-dimensional system, which is a bit bio-inspired. I'm from biomechanics, so biomechanical engineering, so a bio-inspired manipulator. Example, a simple manipulator, of course two-dimensional, right? And I was thinking about this. This is already an interesting manipulator. We sort of use it every day, right? Now, this is the reality. I have some here. And then we usually make a model of things because real life is too complex. It's too complicated. So then we think, oh yeah, the manipulator is fixed to the ground. I see myself as an inertial body, and then you have like two bars connected to each other. You could also, if you from a mathematical point of view, or then you say, oh yeah, this is like a double pendulum. I see two pendula connected to each other, and then they're connected by ideal hinges, no friction, and the bodies in itself are rigid bodies, rigid rods, and that is actually pretty nice model for our simple two-dimensional manipulator. And we want to do dynamic analysis on this. We're not interested only in kinematics, but we want to know when we apply forces, what is the motion, or if we apply a motion, what force do we need? Those type of questions we want to ask. Now, the complete model looks something like this. The bodies have a finite dimension, of course, and so they have some at the center. Let's do it simple. They have a cm. So they have some mass and they have some inertia. Of course, let's do the ground. There is some coordinate system, x and y. This center of mass has coordinates, x1, y1, and phi1. It's a rigid body, so you can place it somewhere in space at an angle. Let's give things a name. This is A. This is B. It also has a dimension. It has a certain length, L1. What else? Oh yeah, and the orientation phi. I draw it again in the figure because it's not really clear in reference to what line is the angle. Is it to the horizontal or the vertical one? Well, this is only the first part. Of course, the second part is again such a thing with a center of mass, and now its position is x2, y2, and phi2, and to be dead clear about what is this angle phi 2, I put it again here. And then we have, of course, a length also, L2 for this body. We have M2 and I2. And there's this endpoint C. The C is the point where the manipulator is reaching out to the world. Of course, we have gravity. And gravity works, of course, in the horizontal direction. My colleague always says that I totally mix up your whole brain now because I still talk about horizontal and vertical and about gravity in the horizontal direction, whereas horizontal and vertical is always connected to how is gravity working. So this is creating confusion. Now, it's not my purpose to create confusion, but why do I do gravity horizontal? Well, if the gravity were vertical, then everything is falling down, and then all things have a negative y component, and it makes everything so negative. And I like positive things. I'm really also in the family. I'm the positive guy always. Where people see trouble, I see opportunities, right? So I thought, well, I see an opportunity here. Gravity is just a thing we don't understand. So what the heck? Let's do it horizontal, right? Yeah. What else? So this is the problem, and then what do we want to know? Now we actually want to know x1 as a function of time, y1 as a function of time. So given the forces, and that in this time that is only gravity, we want to know the angle as a function of time, we want to know the position of body 2, x and y, and the angle of body 2. And all, question?
Do you mean by the horizontal gravity that you've actually taken the physical bit and just tilted it 45 degrees or 90 degrees?
Yeah. I cannot do it with the iPad because it rotates all the time.
But is that what you mean by the horizontal gravity? Or?
What I mean is that I create confusion by saying gravity works in this direction. That is still clear. But now I call this horizontal. And that is not correct. If I would be that correct, then I would say this is the x, the positive x is the negative downward direction.
Okay.
But that fries your brain all the time. At least my brain. So and I want to keep a cool head. So I say, gravity is just in the x. So if I'm going to draw applied forces, they will be in this direction. That's the only thing. And I still talk about horizontal and vertical. Okay. And these positions I want to know with reference to this coordinate system. So those x, y, and z within frame n, the inertial frame. Inertial frame. If you paid attention to Heike, then you have to put every time say, it's in this reference frame, and that's an inertial frame, or this is a body fixed frame, and it's important. Okay. We have sort of a shorthand notation, of course, for that everything is a function of time. We do not write it explicitly, but we just imply that all our variables are a function of time. So we say we have a vector of positions, x1, y1, phi1, x2, y2, phi2, and we have a vector of applied forces at the CM. So that's a force x in the CM of 1, a force y in the CM of 1, and a torque at 1, and the same x at 2, the y direction at 2, and a torque. Now, given these and the system, we want to know what is x of t. So it is, these are given, and we want to know these guys. You can also play do the game the other way around. Say, I say what the motion is, and now I want to know what the force is. But for now we say, no, we know what the forces are. And so if we know what the forces are, what are they? Well, that is super easy here. In here we have, of course, maybe I draw them here. already in. So this is M1G and this is M2G. And those are the applied forces. That's it. So there's here a M1G and there's no Y and there's no torque because the gravity is at the center of mass. That is pretty convenient actually. And then this is M2G and 0. So these are the applied forces. This should be a 1 and that's not clear. M1. So these are the applied forces, they are given and we want to know this as a function of time. And what is the toolbox that we have? Well, the toolbox is our Newton-Euler equations, right? So Newton-Euler equations of motion, EOM, being sum of the forces is mass times acceleration, and the sum of the torques is inertia times angular acceleration, all at the CM. So that should do the trick, right?
Do the two different bodies not create a moment for each other?
I bet they do. One body pulls the other and the other body holds the other one, restricts it. Absolutely. So the big question is, can we write down, given these constant forces, what the motion from this for the center of mass is? Do you know the solution? By head? Could. No, eh? Can you write down the solution by head? Is it simple? Does anybody know the solution? Nope. Okay, how do we find the solution? I mean, we have all the ingredients, right? We defined what the system is. We know what laws to apply. What else is there to do? How do we solve this? What are boundary conditions? I don't know what they are.
Constraint connecting it to the ground is a binary condition.
Okay. But the x and the y of body 1 in point A cannot move, right? That is a boundary condition. Okay, is that the solution to the problem?
That's the boundary condition
That they're connected here. So we have a lot of boundary conditions. How did Napoleon win the war? He didn't, yeah. But I didn't say which war. We are talking about different wars. I talk about the ones he won. So how did he win it? What did Napoleon do? Okay, Napoleon was pretty successful, right? Let's start with that. So he knew his business. We don't take some loser, but we take Napoleon. So Napoleon, okay. What was his whole strategy? So he had a problem. We have a problem, he had a problem. Right? So in that sense, we're alike. How did he solve his problem? Huh? No idea? Classic. Divide and conquer. I don't know any Romans. Romans? Yeah? Which country? Italy? I don't know. Never heard about it. Napoleon, that's the guy. He gave us our name and our home, the street names and the numbers in the street and schools and, well, not really true, but well, anyway. So Napoleon was clear, divide and conquer, and maybe also in the past it was done. But how do you solve a problem like Maria? Divide and conquer. So what do we do in our system? If we have here our multi-body system with the bars which are connected, we apply our most powerful weapon, which is, no, what is the most, that's not a weapon. A weapon is something else. What is the most powerful weapon of an engineer? The? Scissors, of course. Scissors. What would an engineer do without scissors? Right? Well, everybody, no?
I don't use it.
You don't use scissors?
Not for engineering.
Absolutely you do. I know for sure you do. So everybody has been in kindergarten, right? And then you learn to play with scissors. And what else do you learn in kindergarten? Oh, huh?
How to glue.
How to glue, okay. And we will see today, the only thing you need for multibody dynamics is kindergarten's material. You need scissors and you need glue. That's everything you need. Okay, first the scissors. So with the scissors you cut up the body. So you can cut anywhere. I mean, you can take your scissors and you can make a cut here or you can make a cut here. I mean, it's okay. If you cut it on top of there, you get a body like this and you get a body like that and the rest of the system. And then you have introduced forces here and etc. Of course, you have to make intelligent cuts. I mean, only if you want to know the internal forces here, you cut it somewhere in the middle. But what are we going to do here? We are more interested in the motion of the two separate bodies. So it makes sense to separate them at the joints, right? So that's what we're going to cut. So again, now I'm going to try and use this beautiful thing. Ta-da. So we're going to not cut there, but we're going to make our cuts here. So, scissor, come back. So scissor here and scissor here. Or whatever. It's not a very nice scissor. And we can delete those. Oh. Go away. If we cut there, then we end up with two separate bodies and a support, right? So we make two cuts and then we get three parts. So the first part is this support. Second part is, and I'm gonna do sort of an exploded view a little bit, is this first body, and then the third part is this guy. Yeah, let's put some dimensions in it. So this is L1. What was this? This was L2. And this is, oh yeah, do the applied force here, M1G. And do the applied force here, M2G. Now, here I'm really going to draw free body diagrams. So these should be free body diagrams. Then I should have a coordinate system. Well, I can draw it anywhere. X, Y, that's my coordinate system. Yeah, and maybe with an N, but I'm not going to do that now. It's inertial, so I ground it like this, so you know this is the inertial reference frame. But when I cut bodies, then this comes at a price, right? Because there should be something here. What did Newton say? Action is minus reaction or something like that. There's this mutual actions between, for instance, this body and the support. So there is some horizontal force, and so there's the support has a horizontal force here in A, horizontal force in A, and according to Newton's second law, or I lost track of the numbers, there's this equal and opposite force on the support. And then for the vertical, same, and you can choose whatever direction you want, up or down. So VA up, but then if you have chosen that, then here you have down, VA. And we progress to the next body. So here we have horizontal force in B, and likewise on the body here. And I choose to do here up vertical in B and down vertical in B. This is body 1, this is body 2. So these are free body. This is not a free body diagram, but I like to draw your attention to it that if you make 2 cuts that you always get 3 parts. So never forget that you also have this support where the forces are acting on. And since the support is connected to the inertial world, the inertial world can supply infinite amount of forces at an infinite short time, etc. So it doesn't move. So it can supply any force at no penalty. And therefore we need not draw action-reaction forces on this inertia, on this thing. But it's not a real free body diagram. It's not moving. If we want to do that, we add mass to it, and we say the mass is infinitely large, and then I'm not going to do that. That makes things too complex. So let's focus on, we want to know the motion of the system, so we want to know the motion of these bodies. We're not interested in how much the Earth maybe moves. Well, then it's super easy. We start with body 1. We say the sum of the forces is mass times acceleration, and we have to do that in 2 directions. And actually what I'm now doing is accounting. Now, I don't know how good you are in finance, and I'm not. I'm very bad at it. I usually ask my wife to do it. I forget things and so on. But unfortunately, this is also accounting. You have to keep track of what goes in and what goes out, and well, you just have to do it. So, plus HA minus HB plus M1G equals M1 x double dot 1. And then vertical, VA minus VB, no applied forces, right, is M1 y double dot 1. And then now comes this Euler thing. Sum of the torques about the CM is the ICM times phi double dot. So what are the forces? So here is the center of mass. Now it helps sort of to put in the angle, to draw in. This is the phi 1 angle, and this is phi 2, which we'll need in a moment, but for this one. And of course the center of mass is exactly at half of the length, L over 2. So we need to know the sum of the torques at the CM. So, and the only forces, well, this one and this one and this one and this one, they all contribute to this torque, right? And since the angle is in this direction, so counterclockwise is positive. So HA and HB have a positive contribution, both. So it's HA plus HB, and it's times L1 over 2, right? But the distance is of course not the whole distance, it's the projection, and then we need sine or cosine or tangent or those kind of things. And it is not so difficult. If you have an angle phi here, then this is sine phi and this is cosine phi, if this length is 1. That's the only thing you have to remember. And also that I use a shorthand notation. So S phi means sine of angle phi.
Maybe use that as well.
Sorry?
Maybe use that as well as notation.
If you are that clear about what you are doing, I'm okay with it. You may also call sine cosine and cosine sine. But you have to be very clear what you mean. And it's okay. I wouldn't do that about renaming things, but yeah. So what was this? This is the sine, Sine phi 1. And then we have again for the vertical, they go with the clock, both. So we have, no, this was, oh yeah, so that's a minus, right? VA, accounting is difficult. L1 over 2, and then it's cosine phi 1, and that's I1 times phi double dot 1, right? So that is the Euler part for the, so we have the 3 equations of motion now for the body 1. And body 2, yeah, that is super simple actually. It's actually absolutely the same. Sum of the forces is mass times acceleration. Then we have to look at body 2. What forces do we have? We have a horizontal in B and the gravity. So we have the horizontal in B plus m2 times the gravity is m2 x double dot 2. And then for the vertical, we have only this vertical force is m2 y double dot 2. This is a simple equation. And then the torques, well, again we have the horizontal working in this direction and the vertical in the counter direction. So it's the horizontal force in B, L2 over 2 times the, again, the sine phi 2 minus vertical in B, L2 over 2 cosine phi 2 is I2 phi double dot 2. And then if we did everything correct, we're done, right? Because we have our 6 equations. Oh, don't rotate. We have our 6 equations of motion. For the unknown, the things we do not know is all our accelerations, right? So it's x double dot 1, y double dot 1, phi double dot 1, x double dot 2, y double dot 2, and phi. So we have exactly as many equations as we have accelerations. So that's good. Right? Yippee. Can we solve these equations? Can you solve them? Why not?
I think they have to be numerically solved.
Why? I mean, you know what the mass is and the length and the angle at a certain instant. So you know what all these numbers are. You know what the joint forces are. No, bugger all. We don't know what the joint forces are, right? So we have 6 equations, and our unknowns are not the accelerations, but they are the accelerations and the joint forces. Joint forces are unknown. So in our unknowns we have to add, well, how did I call them? Well, I didn't call them, I just said HA, VA, HB, and VB. So these are our unknowns, these 10 numbers. 6 accelerations and 4 joint forces, or constraint forces, or cut forces, or whatever you call them. So we have 6 equations and 10 unknown. Solution. How many solutions do we have? You have 6 equations and 10 unknown. I always say it's a Cole Porter problem. Cole Porter wrote a song and it's called Anything Goes. And it goes like this. In olden days of silken stocking, showing a leg was shocking, now heaven knows, anything goes. If you have 6 equations and 10 unknowns, anything goes. You can put in, you have an infinite number of solutions. Anything goes. And that's a bit disappointing, of course, because I know from experience, if I take a double pendulum in a certain configuration and let it go, it will approximately always show the same solution. So we're missing out on something. What do we miss? Remember your kindergarten days. the glue. Yeah. So how do we find a solution? We need glue. Solution. You have to add the joints again, because all the information about the joints is lost. Or in other words, you have to glue the things together. So I always draw this. It goes like this, right? Glue. So if you use scissors, you always need glue. Scissors, glue. Now the scissors we've done, and through the scissors we've got our joint forces and so on. So what is the glue? So we have to add the joints. And where do the joints come into play is, well, we have cut this thing, so let's look at some cut we made. So we had a support here, that was in A, right? X, Y. And then we cut the body loose, let's say like this, that was the first cut we made. And so this should actually be together. So how can we express that this point should actually, so this point A, this is actually point A, this is O, sorry. That this point A should be here. And the things we have is coordinates here, the center of mass, that's our variables. And we have dimensions, we have a length here, L1. And of course we have this angle, phi 1. So given these things, and given this dimension, how can we say that point A should be here?
I'll express the coordinates in the reference, what's the thing called?
Yeah, that's okay, yeah. We just write down what is the coordinate of XA starting from here. So we say, oh yeah, that is, well, you start here, you start at the center of mass, that's our variable, and then you have to walk backwards, minus L1 over 2, and you have to do a crooked backwards walk, and that's with the cosine of phi 1, right? So that's you walk backwards, and if you are there, then it should be 0. That's your, what we call constraint. So this is your glue. This is the glue you're doing. Glue. This equation. And of course you made 4 cuts in total. And there's also a vertical position there, and that's y1 minus L1 over 2 sine phi 1, and that should also be 0. And again, we have glue for that the two parts are, this was body 1 at point B, and this was body 2 at point B. So this is L1 over 2, and this distance is of course L2 over 2, body 2, and this is body 1. And again, we want to express that this distance and this distance should all be 0. So this is like a delta x at B, and this is like a delta y at B. And we can calculate that, because we can calculate what the position was for point B if we start from body 1. If you start from here, you go here. And you can also do the same. You can start here and go back here. And you say, they should be identical. So how do we do that? We say, well, x1, and now it's plus because we L1 over 2, and that's a cosine. No, I'm not allowed to write cosine. Cosine phi 1. Now we're here, and that's actually xb with respect to position 1. Sort of, it's not completely true. Oh, I hate this notation, I'm not going to use it. So this position should be identical to if I start here, x2 minus L2 over 2, and that's cosine phi 2. Now we want to have everything is zero, like a null terminated thing. So you could say x2 minus x1, and then the other one is well, plus L1 over 2 cosine phi 1 minus L2 over 2 cosine phi 2 is 0. This is one.
Shouldn't they be turned around? One of them?
I turned one around. Right? Did I turn the wrong one around? Oh, dan maak ik weer een min van. Zo. Dank je. Thanks.
Sorry, one of them is missing a cosine.
Yeah, cosine, thank you. Cosine, yeah, and the box. Okay, but the correct things are of course in the book. I'm a bad accountant. And likewise for the y you can write down the same, and you bet it will be something like this. Minus L1 over 2 sine phi 1 minus sine phi 2. Right? So how many equations? We have now in total 4 equations, 4 constraint equations. So the 4 constraint equations together with the 6 with those 6 equations of motion now would be able to have, we have 10 equations in total, 10 equations, and we have 10 unknowns, and if they are linear, the equations in our unknowns, so we have to check that, are they linear in our unknowns? This is linear in the acceleration and the forces, right? Yeah, everything is linear in our accelerations and in our forces, so it's a set of linear equations, a set of equations which are linear in our unknowns, and we have 10 equations and 10 unknowns. So I expect that you can find a solution given that your coefficients are all regular. If you not have too many zeros, then that should sort of work, right? There's only still one small problem. Our unknowns are accelerations and forces, and here our equations are written with forces and accelerations, but our constraint equations, our glue, I see neither an acceleration nor a force there. So it's very nice that we bought this glue, but you can throw it away. The glue is not gluing anymore, right? It's old glue or the wrong glue. It doesn't help. I mean, you could also say green is yellow plus blue. And in itself, it's a correct equation. But it doesn't help us to solve this. What to do?
I can take the derivatives.
Yes. You don't need glue, you need a derivative of glue. It's actually a nice pun. A glue derivative. So let's go to the first one. The first constraint equation was about this position XA, right? So, yeah. Now I'll rewrite it, that's a better way. So let's focus again on, we had this support here in O, and then we had this body here, body 1, point A, and then we had this expression about this distance, XA being x1 minus L1 over 2 cosine phi 1 is 0, and then we say, oh, now we take the derivative of this guy. So what we're actually looking at is x dot A is x dot 1, well, the derivative of cosine is something else. Minus sine, yeah, thank you. L1 sine, oh, I'm not allowed to write sine, phi 1, phi dot 1 is 0. So here now we have the expression for the velocity. And now we have to take yet another derivative because we want to know accelerations, right? So we do x double dot a is x double dot 1. Then this is a product of terms, and I first do this one and then this one. And I do it because then this is constant here. And now I have to differentiate this. And then I get plus L1 over 2 cosine phi 1 phi dot 1 squared is 0. And now finally I have my glue equation on the right level, expressed in terms of the accelerations and of course the angle, but suddenly we also get a speed term here. And that shows us that of course our equation was some force is mass times acceleration. So in order to solve our system, we also have to know at time t is 0 what is our position and what is our speed. And with those two, the state of the system and the equation of motion, we are able to solve. So this speed, initial speed, and the initial angles, they are just constants in our equation. And we have a nice linear equation here. We do that for all 4 equations. And then we get 4 linear equations in the accelerations. If we then form our set of equations of motion, they turn out to be a little bit more complex than we expected, because our variables, let's take a little bit more space. Our variables are accelerations, right? So x double dot 1, y double dot 1, phi double dot 1. It's linear equation, so I can pull the coefficients and the unknowns as a matrix vector product. X double dot 2, y double dot 2, phi double dot 2. And then I have horizontal in A, vertical in A, horizontal in B, and vertical in B. So those are the unknown quantities. And the first 6 equations, which are, is this set, is all equations of motion. So it all has to do with mass times acceleration is forces. And the forces on the right hand side we already know, right? Remember, if we write down our stuff, the only applied forces were gravity. So on the right hand side we see gravity. We see only and gravity was in the x direction. So we see m1g 0, no torques, m2g 0, 0. So those are the applied forces. Then here in this side we have to write our equation of motion, which was for one part mass times acceleration, and for another part constraint forces, horizontal force in A, horizontal force in B. So for instance, if I remember my first equation, that was m1 times x double dot 1, and then something, nothing actually, because it's just a sum of horizontal forces mass times acceleration. But I also had constraint forces. The constraint forces was a horizontal force in B, in A. So here's a 1 for the plus horizontal force in A, no vertical force contribution to the horizontal equation, and then a minus 1, because the HB is minus, and 0. So this is just some horizontal forces is mass times acceleration. Then the next equation was again m1 times y double dot, and then we had the vertical forces. So that is 0, 1, 0, minus 1. Then we had the torque equation from Euler. So that is I1 times phi double dot 1. And now it's becoming a bit more complex, because we had the horizontal in A and the horizontal in B, and with the L over 1 divided by 2, and it was a sine or a cosine, or anyway, it's all in the book. I don't want to make any mistakes by doing it by head. But so slowly this thing fills up and you will understand this is M2, this is M2, this is I2, and here we get coefficients. Yeah, you probably get 1, 0 here and 0, 1 here, and then some numbers here. So we get mass, we get coefficients here, and then we have to add these, the glue equations from here, we have to add here in the bottom. Well, the glue equations have a lot to do with accelerations, and they have nothing to do with the forces. So I can write a big 0 here, there's nothing. Zip, 0, nil, void. No numbers are there. And the numbers here, well, it will probably, the first equation was something like x double dot, so that's a 1. No, y double dot. And there was some L1 over 2. Well, we started with a cosine, then we got a sine, and then we got a cosine again. And I don't know about the sign, plus or minus. Well, I do know, it's plus. We started with minus, and so differentiation we got that. And for the rest, these are zeros. And then you can continue by filling in these lines. The bottom line is that the structure we get is something like this. We have accelerations, we have constraint forces, we have applied forces here, then we have some convective terms you will see, and then here we have mass, here we have a matrix A, here we have a matrix B, and here we have zeros. And the funny thing is that you can solve this set of equations. Although there are all zeros here, you can still solve it. And that's the topic for next week.